So let's talk a little bit about what kinds of systems MapReduce is deployed on. So I don't spend too much time on the system internals, since this is a data science course, not a distributed systems course, but it's good to have an intuition for what's going on under the hood. So there's three types of systems to be aware of, or architectures to be aware of: shared memory, shared disk, and shared nothing. In these diagrams, these cylinders are the disk, these rectangles are the memory, and these circles are the processors. Okay. So shared memory means that every processor has access to all of the memory and all of the disk. And this is what you think about when you have sort of a laptop if it has 4 cores in it. If you have a quad core system, or nowadays if you have 6 or 12 cores in your laptop, this is the model that's being used. This is the architecture that's being used. Shared disk is somewhat less common in, at least in these contexts that we're talking about, although certainly common enough overall, where you'll have individual machines that all access a shared file system. Now that setup is very, very common, but for using that setup for parallel analytics is sort of the domain of high-end commercial databases. So your Oracles and your IBMs will often use a shared disk architecture. Okay. And then shared nothing is really what we're focusing on here, and this is what MapReduce is designed for, and what increasingly and largely parallel databases are designed for as well. Okay. And shared nothing here means individual machines that are only connected by a network. Okay. No shared memory, no shared disk. Fine. So the argument is that only the shared nothing architecture can scale to sort of thousands of computers and beyond. Okay. Because eventually that the sharing of memory or the sharing of disk eventually becomes the bottleneck and limits how many computers you can attach to the same device, or same logical or physical device. Okay. And so learning how to program these massive shared nothing clusters is what MapReduce and parallel databases are all about. And the shared memory machines are perhaps the easiest to program, but are conventionally assumed to be pretty expensive. I should point out that the costs are dropping fairly quickly, so it's getting more and more feasible to buy a pretty beefy machine with lots of main memory and lots of cores, and your problem might fit inside that one. So when you see people deploying Hadoop and MapReduce on fairly small clusters on the order of, say, 10 nodes, you should see whether the data sizes they're processing are actually all that large, right? It could be that the data sizes they're processing are something that fits in main memory on a similarly priced amount of hardware. Okay. So fine. So Hadoop and MapReduce are designed for really, really large clusters. Okay. All right. So this is the context we're in: a large number of commodity servers connected by a high-speed commodity network. And here, you think about a data center. There's a rack that has a number of servers, and there's a data center that has many racks. And this is how you organize your thousands or tens of thousands of computers. Okay. All right. So you're looking for massive scale parallelism that will run, jobs that will run for many hours, even on thousands or tens of thousands of servers. That's really the context we're in. So when you're in this context, an issue that comes up that does not come up all that often in a much smaller context is failures, right? So if you're running a job for a long time on thousands of computers, the chance of something going wrong during that job becomes essentially 100% probability, right? There's going to be something that fails. And so your system of processing, doing this sort of analytics, has to tolerate this kind of failure. You can't roll back to the beginning and just restart every time there's a failure occurs, or you would never get anything done. Okay. So even if the mean time between failure for, say, a disk is a year, if you've got 10,000 servers with multiple disks, or 10,000 disks, let's say, spread across 1,000 servers, or any combination hereof, you're going to start to have failures, once per hour. And you can look up the mean times failures and actually do the math, but there's a couple of nice papers out there that I'll try to put in the readings if I remember. Okay. So failures are what we're concerned about here. All right. So that's hardware. Popping up the stack one level is this distributed file system, and you might see HDFS too, which is the Hadoop distributed file system. So you remember the context here was that MapReduce was proposed in a paper in 2004 by Google, and Hadoop was the implementation of the ideas in that paper. Okay, so we can almost use them interchangeably because the actual implementation at Google has certainly evolved since that paper and is not completely known, right? So when people are talking about MapReduce, they're typically talking about Hadoop or other implementations of the programming model that have nothing to do with sort of scale out. But shared nothing MapReduce can be assumed to be synonymous with Hadoop. Okay, so this is a file system for very large files, and the idea here is that if you're going to take a single file on your own computer, you can manipulate it as a single unit. But if you're going to take a very, very large file and put it on a file system that's on a cluster of machines, then there has to be some layer of logic that knows how to split that into pieces and put those pieces in different machines and keep track of where they are. And that's what this distributed file system software does. So each file is, as you're uploading this data to the cluster, each file is partitioned into chunks that are, say, typically 64 megabytes, although this is configurable. And so each chunk, and this is critical, is replicated several times, right? So there's not just one copy of the chunk. There might be multiple copies on different machines. Why? Because if one of them goes down, you want to have access to the other chunks, okay? And you want to make sure these are spread across different racks in case the entire rack of computers goes dark. You still have another copy of it, okay? And so the implementations here are GFS and HDFS. DFS is the concept, and the implementations are GFS and HDFS. All right, so here's the phases of MapReduce that's a little bit more detailed than the abstract phases that we were talking about when we were talking about the programming model. Okay, so there's a file split here that's read from HDFS, and remember HDFS means it's replicated. There's the chunks could be, there's multiple copies of every chunk, and there's a unit of code called the record reader that breaks that chunk into, I'm using chunk and split sort of synonymously. I'm not a big fan of the term split because it's sort of sounds too much like a verb to me. The record reader parses that split or chunk into individual records. Then the programmers, the user's map function is called on that individual record. And then there's a step called combine that we haven't talked about, but I'll talk about in a moment. Next, actually. Okay, and then the output of these phases are written out to local storage on that node, as we said. So then these regions in local storage, one per key, are pulled across the network by the reduce phase. Then all the regions from all the different map tasks that correspond to the same key are sorted together in parallel. And finally, the user's reduce function can be called to produce whatever output it produces. And then the output of that step is actually written back out to HDFS so that it's replicated. So again, if something goes wrong in the map phase, you have to rerun the mapper. And if something goes wrong in the reduce phase, you have to rerun. You can pull the output from the local storage from the map phase. And if something goes wrong in the overall job, you're safe because you don't lose data because the HDFS are replicated. And if you lose a reducer and you lose corresponding mappers, that's fine. You can sort of rerun whatever you need to rerun. Fine. So the point is that you're guaranteeing for fault tolerance during job execution. All right. And so let's talk real briefly about the combiner. So to think about why we need a combiner, go back to this word count example that we began with. Well, in each case we produced a word and just the number 1. In the earliest version of this, we just produced the number 1. Right. Sending all of these occurrences of word 1. So if word 1 appeared twice, then you're going to get a key value pair with W1 and a number 1 and another occurrence of W1 and a number 1. And you're going to send both of these guys across the network to be sorted in parallel and grouped in order to be processed by the reduce. Well, that's sort of wasteful. You'd like to combine these into a single record, W1, comma 2, and then just send that because it's smaller. Well, you could rewrite your map function to do this, but it's such a common need that you have this capability called a combiner. And so a combiner identifies key value pairs with the same key and lumps them together before sending it over to the reduce side. So it just saves the network traffic. In many cases, the combiner function can be literally the same function as the reduce function, and it all works out. And what needs to be true for this to work is that the function that you're applying needs to be associative and commutative, but I'm not going to say much more about that. Okay, so here's what it looks like in pseudocode. We saw the map function earlier, and we were emitting this key value pair of a word and a count, and we saw the reduce function earlier. But what we're adding new is a combiner function that has the same type signature as a reducer. And again, often in many cases can literally be the same implementation as a reducer. And the only point of this is that it's being applied before sending data across the network. Fine. So here's sort of a summary of a Hadoop job that I like a lot, and this is from a Huivo who's now at NYU Poly, I believe. He's still at NYU Poly. So the data begins on HDFS, and there are these chunks, and the in-part partitions go to map tasks. Now these are, again, not invocations of the map function, these are entire tasks. And the map, each individual map invocation may produce multiple key value pairs, but regardless, the map task almost certainly does, right? So it's going to produce these local sort of colored key regions. And the regions are going to be pulled across the network to the reduce servers. And here in this example, there's only 2 reduce servers. Now, before we gave this example, we sort of showed all the blue ones going together and all the red ones going together. That was a bit of a simplification. What actually is going to happen is that if you only have 2 servers, well, all the hundreds of possible keys need to be mapped to just those 2 servers. So you're definitely going to get a mix going to the same place. And this is where we've been a little bit glib up until now. We've said that you specify the key and it hashes to a particular reducer, which is true logically, but before that, you have to actually get it to a machine where lots of reduce tasks might be running, or lots of reduce invocations might be running. Okay, and so, in this case, the blue guys and the red guys both ended up on the same machine, and the green guys and the orange guys both ended up on the same machine. And then this parallel sort manages that, right? So it puts all the red things together and puts all the blue things together. And then for each individual color, one reduce invocation is called. Okay, and the reduce function is called, and it produces the output partition, and then that output is then written back out to HDFS. Okay. Let me stop there, and I'll pick up here and talk a little bit about parallel databases and how they do query processing, with the point being that it looks a lot like MapReduce.